All right, good. Welcome everyone. So today we have an invited speaker, a recent graduate from Stanford, Francisco Romero. So it's really a great pleasure to have you here. Frankie did a very impressive work on both serverless and um, video analytics fronts, and these are very interesting directions, very hot. Right now, Frankie is pursuing an entrepreneurship dimension post-graduation, which is, I guess, quite common in Stanford. So we are in Singapore. We also are very much interested in innovation, and also are very curious to hear about your early experience and endeavors. So, and also your collaborations with the industry. It's really interesting. So all the experience you can share will be very, very welcome by our group. Thank you very much. Please take it from here.
All right, while I'm sharing my screen, let me see here, find the right screen to share. I think it's this one, let's see. You can see this, right? Oops, yeah. Yes?
Yep.
Okay, great. I'll try to kind of monitor the chat, but please feel free to speak up. Just simply interrupt me. I want to make this interactive, and just so I keep track so I don't go over, what time does your meeting normally end? Just so I keep track of, like, the time and stuff, like, or how much time roughly do you want me to budget for?
I think with the discussion for an hour, but if you need to go
Okay,
early,
no, that's
yeah.
perfect. Okay, yeah, I'm not going to spend an hour talking for sure. I just wanted to make sure that I budget for that. Okay, so thanks, Dimitri. It's really great to be here to chat with you, chat with your students for your group. As Dimitri mentioned, I worked on video analysis systems during my time at Stanford, which really spanned systems, databases, applied AI, and I'm excited to talk to you a little bit about some of the recent stuff that I worked on towards like the second half of my PhD, particularly. And as he also mentioned, some of this technology is now being used in a commercial setting, which I'm also happy to discuss, and kind of like some of the learnings, which I think can be very applicable to your group as well. So let's get started. Okay, so starting from the basics, what is video analytics? So video analytics is basically the ability to extract insights from video, and it typically involves, at the base, machine learning models and some structured data analysis. So some examples of video analytics today are, and you can probably come up with a bunch more on your own, how many cars turn left at night on a Monday? And this is something that somebody like a traffic planner might want to use to be able to understand, hey, how should I be coordinating the traffic lights? For those of us who are sports enthusiasts, you might want to show me Ronaldo's headers when he played for Juventus. But there's also very practical applications. Sports analytics in itself is a very, very popular use of video analytics. And then, for example, this year being an election year in the US, find Jake Tapper interviewing an angry Bernie Sanders. There's a lot of analysis that happens in the news and being able to understand how politicians and journalists are interacting. But I think the key thing, especially for this group, is to note that the approach that I took and that we took during our study of video analytics and really the development of these systems is really an application first one, which is we took some of these queries that you see here, we took the application-centric approach, and we really used that to drive the design of everything I'm going to talk about later. So why now? Video analytics has actually been around for a little while. It's been around for a couple of decades, actually, in some sense. Why is now the time that video analytics is really one of the hottest topics, I would say, especially related to AI? Well, the first thing is, and Dimitri touched on this, there's cameras everywhere now. There's cameras on drones, there's cameras on street corners, there's cameras on cars. I'm certain that all of your phones have cameras, so there's just a plethora now of like video. In fact, 500 hours of video are uploaded to YouTube every single minute. There's just so much of it, and there's just such a great opportunity to be able to analyze it. The second thing is that today there's better hardware. Here I'm just showing a subset of all the famous chips that are coming out from NVIDIA, from Google, from Facebook, from Meta. And what these have really enabled is us to be able to process things as much closer to real time. And you mentioned that some of you are working on the edge. This also applies to that hardware as well. And the third thing is that DNNs have become much more accurate. So really, this is one of the biggest driving forces that allow us to really extract useful insights. So the classic using YOLO or some object detector to be able to identify the objects in the frame, such as cars and people, has been really the bread and butter and the driving force of video analytics for a lot of years. But nowadays, we have a lot more opportunities to do so in a much more comprehensive way, which I'll briefly touch on a little later, through some of these foundation models and generative models as well. So the combination of these three things, I would say, is really why video analytics today has become something that is not just popular, but something that can really make an impact in a bunch of different areas, be it security, surveillance, wellness, health, even things like agriculture and stuff like that. So ideally, what we'd like the video analytics experience or being able to extract this knowledge from video to be is the following. We have someone on the left, some individual who would like to be able to search for, let's say, the fine clips of Jake Tapper interviewing an angry Bernie Sanders. Jake Tapper is a politician. Oh, sorry, Jake Tapper is a journalist. Bernie Sanders is a politician. And ideally, would go through something like the structured querying experience. So using some SQL analytics engine, like Spark SQL, and that would pop the videos that correspond to what I'm searching for. That's what we'd like. And the key characteristics of this are the following. It should be general purpose, meaning I should be able to basically search for anything I want. It should be easy to use, meaning I should not have to be an expert in, for example, SQL to be able to find what I'm looking for. And it should be fast and interactive. Why interactive? Because typically you don't get it right on the first shot. Typically, as many of you who have, if you've ever interacted with SQL before, like some SQL analytics engine, you know that sometimes it takes a couple iterations to get the query right for the results that you're looking for. So if it's going to take you, even minutes or hours to get the results back, iteration is really like a non-starter. So you need it to be fast and interactive so that you can actually use it in the same way that you would a structured like analytics engine. But that's not what it's like today. So what I've worked on over the last couple of years and what I'm going to touch on in some facets today is really this video analytics system. So this box right here. How do we get that structured querying experience for videos? And what really it encompasses is a bunch of different aspects. It requires optimizations across the stack of systems, databases, and query optimization, and AI. And the process is roughly at a 10,000 foot level the following. You need to be able to retrieve the videos and frames from storage. You need to be able to transcode and decode the frames if necessary, if they're not already decoded. You need to perform some query optimization, which I'll explain why in a couple of slides. And then ultimately, you need to be able to execute the DNNs that correspond to what you're trying to look for to get the results. There is a fifth aspect, which is really this bubble up here of how do we even like input the queries and make it easy to use. But in this talk, what I'm actually going, so I could spend hours on pretty much like each one of these topics. I think for this group, what's something that is what I found really interesting and some of the aspects that I think are really still open-ended and I think would be really interesting to this particular group I'm going to focus on the query optimization portion with a little bit of the DNN execution. They're actually intertwined. And then I'm going to talk a little bit about this portion up here, which is I would link it to the folks who are working on some of the things for like how to even do this querying, the LLM, a little bit of the LLM stuff. It's not like, spoiler alert, it's not on LLMs, but it can kind of possibly steer in that direction. And the folks who work on NLP. So I'm going to pause there. This is just like, this is the high level overview. Then I'll jump into some more of the detail. Like, just we'll talk a little bit more about the research. Are there any questions up to now on what is video analytics? What queries, like this pipeline right here, anything at all? Not yet? Okay. So again, interrupt me if anything doesn't make sense or if you have any thoughts.
So maybe I can start. So I guess the DNN execution part is going to, explode as well, right? Because there will be more workflows and I guess interaction with NLPs and like vision parts and like DNNs themselves are getting more complex and so on. So I guess
Yeah,
it's a big simplification of what
absolutely.
it looks like.
It sure is. It sure is. And DNN execution is, there's actually, to your point, this is a 10,000 point view. There actually is the pre-processing, the inference, the post-processing, the management, all those aspects. Some of the aspects that you touched on require a back and forth between the optimization and execution. There's a lot there, absolutely. So you're absolutely right that it's a possibly gross oversimplification, but I've kind of bucketed in that space.
I have another question. So do you
Yeah,
see
yeah.
of dynamism like in this kind of workflows, or it's more of a static workflow?
So that's a good question. It definitely can be dynamic. The reason being, if you make it interactive, then it can be iterative. And once it's iterative, then there is a dynamic aspect to it, meaning what frames you have to touch, which I'll actually touch on in that's a huge part of it is driven by the query optimization, which is why I think that you'll find the next, the next part of this very interesting. But ultimately, what that drives is dynamicity down to the system and resource level, meaning how you manage the frames, how you manage the retrieval, how you manage the DNNs, which hardware should you be picking, and stuff like that. So I covered some of that in Yammer for static pipelines, but I think that more of the recent work has been more on like this dynamic ad hoc queries, and that's really where there's interesting aspects of that need to be still fleshed out.
Thanks.
So, yeah, no, that's
Any
great.
other
Those
questions?
are awesome questions.
If no, we can continue, I guess.
Nope. All right, let's keep going. And you, again, please chime in if anything doesn't make sense at any point. So let's start with, it's mostly a focus on query optimization, but there is, they're not independent of each other, query optimization, DNN execution. So I also highlight that box as well. So like I mentioned before, querying video is expensive. So the accelerators are expensive. Last time I checked, an A100 on GCP, for example, is $3.67 per hour. If you have a bunch of those running, it's going to be pretty pricey. DNNs can be slow. There are some like action recognition that are as low as 3 frames per second. I'm sure most of you, if not all of you, have used things like ChatGPT nowadays. Some of these really large language models, you're not getting the results back immediately. You have to wait a little while, which is what some of you are trying to optimize. So the DNNs themselves still present a big challenge to being able to optimize or being able to achieve like fast and interactive video analytics. But just to give you a sense of how bad it can get, if I wanted to query 100 months of video, it would take, and I did this naively using like that 3 frame per second model. It would take like 14 GPU months to run this, and it's going to cost me millions in cloud compute. So it's naturally not a great solution to do this naively. So really what we want to do is, turns out we want to take like a database approach to query optimization. And we want to be able to optimize the queries as much as possible, where the name of the game is filter as early as possible and touch as few frames as possible as you go down your pipeline. So what that lets you do is ideally you will not be touching a lot of frames with expensive models. That's basically what you want to be, what you want to avoid. Now, this is easier said than done, and I'm going to explain that to you in the next few slides. So today, what it looks like for you to do video query optimization is the following. I'm going to walk you through what it looks like. Let's take this example I just told you. So let's say I want to find clips of Jake Tapper interviewing an angry Bernie Sanders. So what I basically want to do is the two individuals here. I want to basically find all the clips where that look like this across a lot of video. And so the SQL query on the right, you don't need to read too much into it, but basically what it encompasses and requires is three models. I need to use an object detector to detect that there's two people for an interview. I need to use a face detector to detect Jake Tapper and Bernie Sanders. And then I need to use an emotion detector to detect angry. And Mitra, just for like reference, here's an example of where there could be dynamicity. If right now I want to do angry and I say, oh, interesting. And then I want to iterate and say, oh, actually, I want to find like happy Bernie Sanders. Now that's where the dynamic aspect can come in. And so, but for right now, we'll focus on the angry Bernie Sanders. So we're going to look for this. And I'm just going to show you right now how somebody today would have to go about optimizing their query. So the original query that we're going to run is shown on the right. Like I said, you're first going to run object detection, then I'm going to run face recognition, and then finally I'm going to run emotion detection. And what you see here is on a couple of minutes of video, this bar, the time it takes for me to run this is 270 seconds. So that's pretty slow for just a couple of minutes of video, just to identify all the instances in which of my query. So let's see how we can optimize this. I'm going to try to meet an 80% accuracy target. So it's the dotted line, where 80% accuracy in this space, the way we measure accuracy is with respect to the original plan. So you can also think of it as like how much error or like degradation of accuracy are we going to accept? And what we're going to accept is no more than 20% error degradation or an 80% accuracy compared to this blue bar. So first thing we're going to do is we can do a standard predicate reordering. What that basically means is we just want to find the best order of the models to improve our performance. And the reason this works is because, like I said before, there's some models that can filter more aggressively early on. So for example, here, object detection running first is not great because most frames will have two people in them. But if I run face recognition first, we see that this is better because there are less instances of Jake Tapper and Bernie Sanders in the frames. So by flipping the order of object detection and face recognition, we see here that we can get a 5.4x better performance by just simply flipping those. And I met my accuracy target. So that's a pretty good option. But can I do better than this? Another optimization I can do is model replacement. So there was a work that I did several years ago that basically focused on model variance. And many of you may be familiar that there are different versions or variants of models where there can be a cheaper but less accurate model that can potentially run in place of a slower but more accurate one if the cheaper one is still sufficient for accuracy. So in this case, for example, I can just run a cheap emotion detector instead of the more expensive emotion detector. And what we see here is while it doesn't really improve our performance, and it also does not meet our accuracy threshold. It barely doesn't meet it, but it doesn't meet it. So this actually would not be a replacement that we would want to do to find in our particular query. But instead, if I replace the object detector, then it turns out that that works great. It actually improves performance by a little bit, 1.1x, and it does meet the accuracy threshold. So this is a good optimization that we can apply on top of the predicate reordering. And then the third thing that we can do is we can use filters. So the filters, the goal of these filters is basically they're cheap models that can filter frames that do not contain what we're looking for. So let's just look at filters for face recognition. So the first filter that we can consider here is what's called a hard filter. And its job is basically just get rid of the frames, detect the frames in which there are no faces, and do not send them to the face recognition. So this is where there's also, again, bringing up the dynamicity, Dimitri. There's a little bit of dynamicity here because you don't know necessarily what's in your video, but we're going to try to use this to filter frames where there's no face, because if there's no face, there's no point in running face recognition. And what you see is, while it does meet our accuracy threshold, but the performance decreases. And the reason why it decreases in this case is because all the frames have faces in them. So it's not doing any filtering. So, and in this case, this is not something that we would want to run. It's just adding more latency to our query. But you see that if we use a similarity filter, so what the similarity filter is doing is it's just doing a simple computer vision pixel-wise comparison to try to find, compared to a reference image, if there's Jake Tapper and Bernie Sanders. It meets the accuracy goal, and it's very fast, so it gets rid of a lot of frames that do not contain either of the two, and then improves our performance. Question, Dimitri?
Yeah, so actually there seems to be a lot of sources for or needs for some resource orchestration where you can shuffle these filters around because they probably add a latency with like a good effect or maybe not so good effect, right? Depending on how much similarity is there, depending on how many faces are there. So you probably want to allocate resources in a smart way depending on the dataset and the query, right? So, and if we take like geographically distributed, CCTV or something, in real time, like TikToks, web streams or whatnot, then I guess there will be a lot of needs for, dynamic uh, orchestration of resources.
Yep, that's right, exactly. So there's a lot of dynamicity, and I'll touch on a little bit because naturally, I mean, like, peering under the curtain a little bit. Naturally, the question is going to be like, how can we even like figure this out? Like, how do we figure out what should we be using? Which is the whole premise of this work. But you're absolutely right that there's interesting challenges in, not just resource allocation, but figuring out like what are the resources that I should be allocating in the first place for this. So if you hold on just a little bit, I'll touch a little bit on how we did it here. And naturally, I think it actually might spring up a few ideas on your end for how you can do it, especially on the edge and stuff like that, which is not something we've considered. So definitely it's ripe for innovation. But yeah, so just finishing up on this slide. So what you see is that it improved performance 1.5x. And overall, from the leftmost bar to the rightmost, I've improved performance by doing all these optimizations by 9x. So, and still met my accuracy goal. So that's pretty good. That's really great. And as you can tell, optimizations work well. And that's why in the community, in the systems and the database community, there has been a lot of optimizations proposed. There's been things on model variance, on sampling, indexes, specific types of queries like aggregation limits, object tracking, binary filters. There's been a bunch. I didn't even list all of them here. But the thing though is, while these point solutions are great, and this is kind of going along with what Dimitri was bringing up very astutely, is while point solutions are great, the problem is I need to decide which ones to use manually. So as you saw there, I went through 6 different plans. Actually, there are nearly 100 that you would have to consider if you consider all the different permutations. And the best plan is query and dataset specific. So for example, the HAR filter did not work well because all the frames had faces, or majority of the frames had faces. But there can be a data set where there's very few faces and that filter will work well. So what is limiting this end-to-end optimization that things like Spark SQL give you? And it's twofold. You can express domain knowledge to a system. and the systematic way to explore this domain knowledge is missing. So in other words, there's basically no system today that even if it could, even if you told it what kind of optimizations to potentially apply, it has no way to know when and how to apply the optimizations. And so to do this, what we did is we proposed optimizing the queries with declarative relationships. So to be able to have a way to declare what kind of optimizations, to be able to express domain knowledge, came up with relational hints, which are a declarative interface for expressing machine model relationships. And then to be able to use that domain knowledge during the query optimization, we came up with a system called Biva. So Biva is a system that uses hints to optimize video analytics queries. The end-to-end workflow is shown here. I'm going to walk through first hints and then the query optimization and execution stage of like basically how do we pick and how do we know what to apply in the second part. So up to here, before I dive a little bit into each one of these, are there any questions or thoughts?
So this whole pipeline is, as you said, like about the hard filter. So we are applying this pipeline for specific tasks. Like we have already a specific data set of video, like a whole news programs, for example, and we are trying to like crop it to just show the interview, for example, right? So I was wondering if we can use it for example, like out of all like TV program, the whole like from 12 to 12, for example, extract the specific stuff. So while in this TV program there are much more stuff happening, so it's much broader set of images to consider.
Oh yes,
So,
yeah. So you don't, yeah. So sorry if it was a little misleading. You don't need to crop it to the specific parts. You can. This works for any video data set that you throw at it, and as I'll talk about, it will automatically figure out based on what the video content is, what optimizations it should be applying. Is that your question?
Yeah, kind of. So previously you stated essentially like very static stuff. So you essentially evaluated the we showed the evaluation of 6 different pipelines, which are static, but with this stuff, you are based on the content, you change this pipeline.
Exactly. Yes, exactly. So what I walked you through previously is how you have to do it today because before the system existed, and you have to do it like that because there is no optimizer that can automatically do this for you. But now I'm going to show you how the system automatically does everything I just described without the user having to figure that out.
Yeah, great.
Okay. No, that's a great question. Okay, so first I'm going to talk about the relational hints. And this is basically how you describe the domain knowledge or optimizations to the system. And then I'm going to touch on how the system uses those to do the optimization. So there's two relational hints. The first one is model replacement, or what I call a can replace hint. And it's applicable if the two models have the same output format and at least one common class. So the same output format is, for example, if both produce labeled bounding boxes. Simple as that. And at least one common class, like for example, if they both can detect like dogs. So here's an example to make this really clear. Let's say that I would like to detect a basket being scored in basketball. Today, the way that you would do that is probably pass a couple frames through an action recognition model, and then the action recognition model basically can just output basket scored or not basket scored, and I can just filter by basket scored. But as I mentioned before, action recognition can actually be pretty expensive to run. It's one of those models that it can be as low as like a couple frames per second. So an alternative way that I could run this is the following. I can use optical character recognition, and I can basically crop the frame that you see on the left to just show me the score. I can detect the numbers, And then whenever there's a change from one frame to another, for example, 86 to 87, I can basically label that frame as a basket being scored. The way I would express this optimization or this sort of optimization to a system is as simple as the following. Create the hint that score change, OCR, optical character recognition, can replace score action recognition. And what I want you to note is that a system itself is probably not going to figure out automatically how to do this. Meaning it's a human who knows, hey, I know a different way to detect the basket being scored that enables you to be able to express this one-liner to a system, which I will talk about that specific system shortly, to be able to use this as an optimization. The second hint, the second of the two hints, is input filtering, or what I call a CAN filter. And you can use this when models have different output formats. So for example, one produces label bounding boxes and one just labels the entire frame. Or if they have the same output format in disjoint classes. So say one does not detect dogs and the other one does. So let's go back to our example of wanting to detect, let's say very specifically, Bernie Sanders in the frame. The way it's done today is to use a face recognition model that's going to produce bounding boxes. And in this case, as you can see, it has detected that there's two faces and one of them is indeed Sanders. So the problem with this is that it can be unnecessarily expensive to do, especially if a lot of frames have faces other than Bernie Sanders. Kind of like I already showed you in the previous, in a couple slides back. So a cheaper way to do this is I can first search the transcript and find instances where Senator Sanders is mentioned, and then I could just extract those and map those to those timestamps to frames, and only pass those frames to the face recognition to run. So again, the transcript search is being used as a filter for face recognition. And so intuitively, that means the way I can express this to the system is that transcript search can filter for face recognition. And once again, the system is not going to figure this out automatically. This is something that is domain knowledge that a person is going to describe. So there's just two types of hints. And while that seems pretty simple, it turns out that two is pretty much all you need. So this actually captures a ton of optimizations. In fact, all the optimizations that I previously showed you, some of which I show here, are captured by these ones. So can replaces captures optimizations that were proposed by papers that talk about model variants, proxy models, indexes, stuff like that. Can filters, binary filters, or particular area expertise, such as like, hey, using motion detection to detect if there's a car in the frame before trying to run, like, is this car turning left? Or transcript search. So what this actually enables is very significant optimization opportunities, and I'm going to show you that in the next couple of slides. But before I do that, are there any questions on these two hints, on can replaces or can filters?
So with the example of transcript search, that means that we need to have these transcripts. So it's pretty narrow use case, I'd say, although still pretty powerful in specific cases. So yeah, so I suppose it's viable because it's some local expertise in some areas when we need it.
Yeah.
So which can, but still it significantly restricts the applicability of this stuff. So for example, if we are trying to find this interview from the whole TV program, some parts might not have the transcripts. Although we can just ignore it and say, if there is nothing there, then there is no Bernie Sanders there as well.
Yeah. So you're absolutely right. And to your point, there's some cases where some of these optimizations are not applicable. So I just gave some examples, but it obviously depends a lot on the query and stuff. So the can filter, the example that I gave here in the previous slide, those are not the only can filters. those are not the only can replaces. And obviously sometimes, you know, there's a lot of cases where transcript search cannot be used. For example, like in like CCTVs, a lot of times they don't have audio. So like you cannot use a transcript search. But CCTVs, you can use motion detection, for example, to detect that there's motion and stuff. And that's something you would describe with a CAN filter. So when you apply them, the filter, when you apply the optimization is very dependent on the video. And that is exactly why it is so hard to optimize video analytics queries, because you need to think about that and figure out when you can do it and how to do it. And now I'm going to show you how a system can automatically do that for you.
Yeah,
if that makes
because
sense, if that answers your question.
It's yeah. It's more or less because essentially we're asking for additional media types in addition to the video itself. So like with the with this transcript, with the motion detection, that is essentially like a separate channel of media.
Yeah. But well, motion detection can be done just from the frames, but the transcript search, you're right, that you do need to pull the, you know, the audio stream out and stuff. And, you know, if you have the transcript, great. If you don't, but you can get it, then the system, as you'll see, can figure out, hey, how, like, what would it take me to do that? The same can be done with some of these proxies and indexes, like, do you have the index or not and stuff. But that's also a very interesting area, which I'll touch on towards the end, of like using all these, you know, sources of input as ways to optimize queries is something interesting. But I think the main takeaway from this is that you having to figure out when should I use it and not, even if you could come up with the query, or sorry, with the optimization, is hard. And having a system that can automatically do that for you is really the key to being able to achieve general purpose video analytics. So, which I'll talk about in a few slides. But this is a great observation. That's absolutely a great observation.
Yeah, thanks.
Awesome. Okay, let me talk now. Now that I just told you, okay, I can now propose potential optimizations that could then be used. Now let's see, how do I actually use these optimizations to optimize my queries? So the first step in this whole process is plan generation. So the challenge here is, how do I incorporate the hints, the relational hints that I just told you about, into building my query plans? So I'm just going to give you a simple example here. So there's two models in my query. There's model A and there's model B, and each one has their corresponding search term. So I'm trying to find where from model A, it matches A, for example, model B, it matches B. You can imagine this is, for example, like face recognition and object detection. So the first thing that Biba is going to do is it's going to generate a model tree, as is shown here. So for example, A will run before B. And then it's going to pass, it's going to permute the predicates and exhaustively apply the hints that I just described to you. And it's basically going to generate additional plans to consider. So for example, if I just do predicate reordering, it's going to flip A and B. If I apply the hint here, C can replace A, then it's just going to replace A with C, the yellow circle right here. And then if we use the can filter hint, then it's going to just apply a new node, or it's going to insert a new node D in front of B, and then that's going to run in addition to, that's going to run before C, and so on and so forth. So it's going to do this exhaustively. And what this allows us to do is take the hints, incorporate them into queries, into the query plan, and have additional plans to consider that use the hints. So for example, in like the last few, some of these would be like, hey, I'm going to insert a potential transcript before running face recognition, or I'm going to run a cheaper like object detector or action recognition. So then once I have this, I have a bunch of plans. That's great. But the question is, how do I pick the best plan that meets the user's requirements? And I think this slide right here is really probably going to be the potentially most interesting one to a lot of you. The question is, how do I, again, like of those plans that I generated, how do I find the one that is the best to meet the user requirements, where best depends on what you want to optimize for. If you want to optimize for cost, performance, perf per dollar, whatever it might be. It doesn't matter what the optimization, like what you're trying to optimize for. What best means to you, the same process will apply. So the first thing we need to do is you need to be able to estimate accuracy. And this is because, you know, the user has accuracy goals, they have error like degradation that they can tolerate. And to do this, we use a canary input. So canary input is a short clip that is representative of the user's query. So we use this when comparing the original unoptimized plan to any newly generated plan. And this is just to get a sense of, hey, what is the accuracy of this plan that I'm going to consider? And does it meet the threshold? After this, Viva is going to estimate selectivity, where selectivity just means like how many frames match what I'm looking for, and the cost. The cost is given by the following formula, which is the sum of the product of the latency of the model I'm going to run on the particular hardware platform that I'm going to run it, times the number of frames that I'm going to process, where the number of frames to process is based on the model that ran before it. And of course, the first model that runs is going to run all the frames, process all the frames. And once I compute this for all the plans, I can select the best plan based on these requirements, like I mentioned, which is simply ensure like the argument such that it meets the accuracy target. Now, two things to note from this slide. First of all, this is actually done very quickly in Viva. It's less than 2 minutes for hundreds of query plans over an hour of video. And to do this, there's some pruning techniques that we apply, basically like trying to estimate accuracy and cost as we go. And the second thing is this formula here for cost per plan. It's actually simplified a little bit in this slide, where it actually, and in the paper, you know, we have the more elaborate one, but long story short is it actually factors in the cost of the hardware that it's going to run, the model's going to run on. And so it can factor in like, hey, should this model run on a GPU? Should the next one run on a CPU and stuff like that? Which is really where I think a lot of you might have interest in terms of like the dynamicity and why serverless computing makes a lot of sense for this. But that's really what's going on here. So I'll show you a couple of results. There's actually just one result after this, just to give you like to whet your appetite. But is there any questions about this? Or basically how we go from, hey, I have these hints that I would like to potentially use in my query to optimize my query, and then the system saying, okay, I'm going to generate possible plans using those hints, and then I'm going to pick the plan that is best given whatever you want, and then still meet your accuracy. Any questions around this?
Yeah, hi, here is Norway, and I have one question about the first step. The estimated accuracy using canary input. My first question is why the canary input works.
So the canary input, which is something that is done actually in a lot of systems work, is basically it's representative of what you're looking for in your query and like what you're searching for. And so it serves as a way to compare what the unoptimized original plan is going to give you to all the other plans that you're considering to use. And
yes.
So it's a way to measure, yeah.
So
like
so
false
here,
positives, false negatives and stuff.
yeah. So here is implicit assumption is that the distribution of the canary input is similar as the distribution in deployment, right?
So canary input is just a small clip that
Okay.
it only contains what you, it's like literally a couple seconds that just contains what you're looking for. And so that's why you can just use it to compare directly and then to compute your accuracy from there.
Okay, so and I'm concerned that maybe in deployment we will face the domain shift problem. Yeah, the accuracy is not very stable when deployed in the practice. Yeah, because for example, if your model is trained for the image or for the video in some domain like daylight, and however your video is recorded at night, and maybe the performance is not satisfactory. So here the canary input is should be selected carefully, right?
Yes, that's right.
Okay.
And so that's something we talk a little bit about in the paper. It is dependent on what the user is. So for example, if that kind of variability would show up, then when you're using this canary input, you would want to consider that. Maybe give it like a mix of, I don't know, like part day, part night and stuff. I think so that is one thing that we set in this paper. Basically, like the user presents a canary input and that canary input should be representative. And it's kind of like, if it's not, then obviously what you may get later on is it may not meet what you're looking for. I think there's definitely future work that we think that could be there for one, detecting if it's a good canary input, and two, being able to automatically select the canary input potentially dynamically. So
Okay.
it's a great observation.
Yes, thank you.
Yeah, I think it's a very good comment. I think what you're talking about in this slide is similar to offline profiling, basically, right? But for every kind of offline profiling method, we can also come up with something that would be real-time profiling, dynamic, right? So technically, like
So-
for the weather change or like day, night, I don't know,
Yeah.
cloudy, sunny, we can somehow get insights into what's happening,
Yeah.
right?
Yep, exactly. And I'll say though that part of this, so the canary input is dependent on, of course, like the models and all this other stuff that you're using. And the number of frames to process and selectivity estimation has to happen in like online, because it's dependent on the inputs that you're giving it. The latency of the model, that can be done offline, but to your point, like some of this can be done more dynamically in the sense of like, hey, like this canary input doesn't seem to be like, the accuracy seems to be deviating or whatever it is, like the selectivity seems to be deviating. That's not something we explored, but it's definitely something that we know is a potential limitation that we can improve on. Which, I think the fact that you guys are thinking about it means, you're thinking in the right directions. I think that's great. So, that's right.
Can I ask a question? So,
Yeah.
the number of frames to process, for the number of frames to process. So, in order to know that number, you need to know how many frames were filtered out by the previous models in the pipeline, right?
That's right. Yep.
So-
And that's what we do online
Okay.
in selectivity estimation.
So you estimate that on a subset of the data, or how?
Yep, that's exactly right. And that's kind of like a standard thing to do. That's what your typical query optimizer, like cost optimizer, will do in a database. We're just doing this over using like AI models over a small subset of it, like 3 to 5% of the frames. And the nice thing about selectivity estimation is you can run it in parallel. So in other words, you can estimate it per model, and then you can just use the statistical model to basically estimate it for all the different permutations. So you don't need to run it like if that makes sense. I just need to estimate it per model, and then I can just basically, it's basically like a fraction of like, hey, how many do I send to the next stage? If that makes sense.
And yeah, okay. I have another question, a bit more general.
Yep.
So in video analytics, how common is it to use like metadata, like to annotate the videos? Like for instance, if you have some frequent queries, you may annotate the videos, like say this video contains Bernie Sanders, because I imagine it's much faster to filter through metadata rather than video.
That's a great observation, and it's definitely used. And I think that's why the relational hints can be something powerful. So for example, you could just say, hey, if in my metadata tag it says Sanders, you can map that, say, hey, I found Bernie Sanders in the frame. And that's going to be extremely cheap. Your latency is going to be probably close to 0. Not exactly 0, but pretty close. But that's also why managing the metadata alongside the video is important. So to answer your question, it's common, and it's something that is definitely taken advantage of. And it also fits very nicely into the realm of relational hints.
Thanks.
So these are excellent observations.
I can also guess that this annotations can come not just from the you know, when you run your queries, but also from I don't know, some early pre-processing or some, I don't know, data preparation.
That's
Maybe even at sensor level, right? Where the cameras are.
That's right. That's right. That's
Because-
absolutely right. And yep.
Yeah, because actually cameras are not just CCTVs. I mean, if you are talking about like the ones that deployed by the road, there are actually a bunch of sensors inside. So some of them could be like video cameras, some of them could be event cameras, right? That transmit change pixels. Some of them could be I don't know, infrared or some other
Depth.
kind of
Depth and stuff
cameras
like
that
that.
can help annotate,
Yeah.
for example.
Exactly. That's absolutely right. And that's one of the things that's cool about this work, that we were like, hey, it doesn't all have to be DNNs. There's a lot of opportunity to filter using metadata, using other forms of telemetry. And you're absolutely right. The name of the game is honestly like touch as few frames as possible. And that's, you know, all the observations you just made are absolutely correct, that you can extend this out to that. So, and it fits very nicely in this ecosystem, this not even ecosystem, this system and the framework. So yeah, these are excellent observations. You guys are spot on. It's very cool to hear. So I'll show you just one result just to kind of whet your appetite. So I'm just going to show you a little bit. So we implemented this on Spark. We played it on Google Cloud. The videos I'm going to show are 1 hour, downsample to 1 frame per second, which is pretty standard, 360p. And we'll look at 4 different applications. So cars turning left with people in the intersection at night, a traffic camera, a traffic application, Tapper interviewing angry Bernie Sanders, which is what I've been using throughout this talk, LeBron James dunks, and then non-white females over the age of 19, which is a bias application using the conversational bias data set from Facebook. The number of hints for each is variable, as you can see, and it ultimately results in different numbers of plans. So the number of plans is dependent on the number of hints and the number of dependencies of the models. So for example, cars turning left, I cannot run the left model, basically like object tracking, if I don't first run the object detection. So that's why there's a dependency there. And then here I'll show you just an example of some of the hints. So for example, motion detection can filter for object detection. I don't want to check to see if there's cars turning left if there's no motion, for example. You can build cheap indexes for motion detection. I can use a similarity detector, as I talked about before, to filter for action recognition. And then the last one is actually a kind of interesting one, where now you have these models that have like prefix and suffix layers, where the prefix layers are all common layers, and then the suffix layers are things that get like fine-tuned. And so you can use this where the prefix layers are all common, and the suffix layers you have specific ones for age, for race, and for gender. So here I show you on the x-axis the 4 applications I just told you, the 4 queries. On the y-axis, it'll be query speed up. There's 3 baselines. So there's upper PR, which is what is the worst case predicate ordering of the original query using no hints, which is basically how bad can it be if you do no optimizations or if you optimize the wrong way. Best PR, which is the best case predicate ordering of original queries, meaning if I apply no hints, but I find what is the best ordering to give me for that meets my accuracy and improves my performance. And then a recent work by some folks from Georgia Tech called EVA, which does predicate reordering and specifies the model per accuracy. So meaning if you have a high accuracy goal, which in this case you do, of 90%, it's going to use the most expensive models. I have some other results in the paper that like show like, hey, as the accuracy varies, like what does it look like? And it still improves on EVA, just for reference. But here I'm just going to show you just this one case where it's the accuracy goal of 90%. And what you see is basically that Viva achieves up to 4.8x speed up by using relational hints automatically, the way that I just described to you. So what you see here also is these performance improvements are inclusive of the time it takes for the planner and optimizer to run. So as I mentioned, we do some pruning to keep these overheads low. So why does it work? So for traffic, you see a big improvement because Viva figures out I can use a faster brightness detector for detecting day and night, and object detector. These are can replacements. For news and sports, it uses a proxy index that was proposed by some folks at Stanford. And the bias one uses the model layer sharing approach that I told you about, the prefix suffix layers. And then oh yeah, so news and sports both use the index, and then bias uses the prefix suffix layers. So the point here being this, by automatically figuring out what hints to use and in what order, we've improved performance, we've met accuracy goals, and we basically don't have to do this hand tuning optimization that is really painful. I don't know if there's any questions about this slide, or like I said, this is just one result. There's a bunch of others I'm happy to talk through offline and stuff like that, but just to give you a sense of, yes, it works. Okay, very briefly, this is kind of what you were mentioning, Dimitri. I just have one slide on this just because I kind of, I guess, prefaced some of your questions. So it still can be very expensive to run things online, even after I've applied all those optimizations I just told you about. So it does make sense at ingest to do some computation that accelerates the queries. So some things that are commonly done, you can create embedding representations and cluster. You could build some offline index using a cheaper model. So for example, I can run a very cheap object detector, and then if I find, basically say like, what are the top 5 things that it found? And then if what I'm looking for is in those top 5, then I can just run a more expensive model online. I can extract motion vectors if I want to be able to do like object tracking later on. On the right, I show some pictures of a work that came out a couple years ago from Washington and Microsoft Research that basically explored this trade-off. And as you can see, I can they show there's a Pareto curve of, hey, if I can spend more time optimizing at ingest, and then it will spend less time at query time. I can spend more time at query time and have cheaper cost at ingest. And then there's a balance point where you're kind of in between the two. So this is just, I just show you the slide just to give you a sense of like, yes, there's still a bunch of optimization you could do. And I think the big question, which is what I have here, is you want to trade off accuracy for performance and cost. There's a lot of point solutions, but you need to be able to capture the domain knowledge to use them automatically. And then you want to be able to figure out, which I still think is an open problem, that's why I don't go too much into it, how do we speed up query performance by doing useful work at ingest? Let me see, there's a question, how often do I adjust my best plans? Do best plans need to change when the data set changes? Yes, they do. Though they can change depending on the data set changes. That is why there's a dynamic aspect to Viva that figures out, hey, based on the data sets, like estimating selectivity and accuracy, it automatically figures out what is the best query plan to be using. I'll note that you mentioned streaming. This is not used in a streaming setting, although it can be, I'm sure you can adapt it to it. There was a work several years ago called Video Storm, that did a little bit of work on this. Let me know if that doesn't answer your question, but long story short is yes, because it changes based on the data set, that is why we need a system like this to automatically do these estimations and choose the best plan based on that.
Oh, sorry, I have another question. So for the hints, are they based on domain knowledge, or there will be a pool of hints that you select every time you want to process a video?
Yeah, so they are, let me see this picture. So if you see this picture here, hints only need to be proposed once, and then they go into kind of this table, this bank, and then I didn't talk about this, but there's a step actually before plan generation called hint validation that figures out what are the applicable hints, and then it figures out, so what are the applicable hints that I can use for this query, and then it uses them for plan generation and stuff. But then, so to answer your question, it is based on domain knowledge, but they only need to be specified once, and it's not once per query, it's once per relationship. So the system basically stores them and then figures out when to use them.
Okay, thank you.
Yeah, okay, cool. Okay, let me, if there's no other question there, I'll spend I just have like 2 more slides, and then I'll ask for any other questions after that. Just because obviously it's a little bit of a harder topic. I briefly want to touch on this little bubble right here, which is like, hey, how do you even describe the queries in the first place? Which I think is a little bit of a barrier to entry in the beginning. So recently, there's been a lot of, and some of you may have heard of this, like there's vision language models that represent natural language and images in the same embedding space, and they've been used in a bunch of different domains. So for like image classification, object detection, video understanding, and each one has their own types of. This is just a subset. By now, there's a bunch more. And the general premise is as follows, if in case you don't know. So let's say I want to detect a photo of Lionel Messi, and I have these 2 pictures here. The pictures will go into an image encoder, and this is all in one model. So you have the image encoder, you have the text encoder, text goes into text encoder, images go into image encoder. And what it basically does is it produces embeddings that can be directly compared to each other using cosine similarity. So what you see is, the picture of Messi and the text, a photo of Lionel Messi, have a pretty high score of a pretty high cosine similarity of 90%. Whereas the other picture with Mbappe has 35. So it's not matching a photo of Lionel Messi. It's not going to be 0 necessarily because Lionel Messi is associated with soccer and then or football, and Mbappe is as well, but you get the idea. And so then in one slide, just to summarize what we did with this, is we wanted to be able to produce relevance, meaning like matches your query, and diverse results using these VLMs. And the challenge of this is you need to do prompt engineering to produce relevant results, meaning you need to figure out, hey, how should I describe my query in order to be able to get like good results? And even when you get the results, as you see on the left, like up here, you get a bunch of duplicated and low quality frames that you need to be able to sift through. And so we proposed a system called Zelda, which stands for Zero Shot Expressive, Relevant, and Diverse Video Analytics. And it had a cool name as well that one of my co-authors came up with. And the general premise of it is it does what is shown on the right, which means it produces results for cars during daytime at traffic intersections. It produces different types of cars, different, more diverse frames. You can see some of them are during the day, some of them during the night. And the way it does it at a high level is it has these steps that basically, these stages that allow it to retrieve relevant frames given a natural language query input, automate prompting to improve accuracy, and get rid of the frames that are low quality. So for example, something's kind of blurry, it automatically gets rid of that. And then it returns the high confidence frames while also producing diverse results for top K queries, where top K can be, in this case, it's top 4. And then on the bottom, I just showed an example of by augmenting it using some automated prompt engineering, we can improve the accuracy metric, which in this case is average precision at 10. So this is just, I know it's one slide, very high level, but I just wanted to give you a sense of, hey, this is another area where we've also touched on, which is on the query optimization, but using natural language as input, which is everybody knows is really where we're headed to be able to explore visual data. So I'll jump to the next slide just to highlight it, and then I'll take any questions that you have about this. But there's a lot of stuff left to explore. I know when I was a grad student, I loved this kind of like little cheat sheet of like, hey, where could I take my research next? What should I be looking for, especially in this domain? So I didn't touch as much on the first 2. Storage for video, I still think is an extremely important topic, and especially in the serverless domain, being able to optimize, like, how do I retrieve? How do I manage when it should be like a lower versus higher resolution and stuff like that? Where should I store it locally, remotely, stuff like that? What do I do at ingest? There's a lot of new cool models these days. Generative AI has really put like multimodal LLMs that can even like you can search directly in the LLM for some stuff in the video. Being able to identify deepfakes is a common application that I've heard for video analytics these days. Being able to figure out how do you fine-tune vision language models for what you're looking for. And finally, because this is a systems group, I think one of the key aspects is building infrastructure for the varying and occasional high throughput demands that video analytics have. That's why serverless makes a lot of sense for this. But I think that that's not the end story, especially because you need to have and oftentimes expensive hardware like transcoding and ML hardware that has to back it in order to make it interactive. So this is, the next slide is basically just like, thank you very much, but I'll pause here. I'll leave this slide up just so that, in case you have any other thoughts, and I'm happy to, at this point, answer any questions or, yeah.
Thank you, Frankie. This is really, really interesting. I think this is very inspirational talk, and we had a lot of discussion.
That's great. No, I agree.
Seems that there are a lot of directions to explore, which is amazing. What I wonder is, from the systems researcher perspective, what are the available open source artifacts or tools, methodologies, frameworks, data sets that we can actually use? And also, who are the stakeholders from the industry who could be interested in this kind of research? I wonder if you can share some experience with us.
Yeah. So in terms of the open source in the world, some of the work. So we have somewhat of an artifact that's a little bit older on Viva. It is online. You're welcome to check it out. I can send you a link after. And like I said, it's a little older, but I think especially for the query optimization stuff, it might give some really good ideas. I think that in the open source, there's also Eva itself. The other work that I compared against is also open source. That's not serverless, but I think honestly, any data flow serverless framework, or even I'm sure, well, we kind of had this with, I guess, DG and Beehive and stuff, but any of those should be relevant. For the data sets, that was an interesting question for us, honestly. There are some published works that have released these open source data sets and stuff like that. Some of which you can refer to in the paper, there's specific links to them, some works from Stanford. There's some works from this aerial video data set. There's things that are more for robotics, but it's still Ego 4D and stuff like that. They all serve the same purpose. Honestly, a lot of the videos came from YouTube. There are cool tools like YouTube. I don't know if you've ever heard of YouTube DL or something like that. We downloaded a bunch of videos from there because a lot of them are, and that's what a lot of researchers honestly do, because you can get for example, entire playlists of relevant content and stuff like that I would highly recommend. I mean, honestly, that's where we got a lot of their footage. And that also makes it, easier for other people if they want to point to how do I get that video? Well, you just point them here's the video, easy to reproduce. In terms of industry, I can definitely tell you that there's a bunch of relevant stuff. So obviously there's the folks who, I'll just list off a few. There's the security and surveillance aspect, which is what we're very interested in, especially our company, and for security, defense, and all that other stuff. There's a lot of video being produced there, not just from CCTV cameras, but also body cameras, dash cameras, drones, which drones obviously overlap with the edge. Healthcare, nowadays, especially after the pandemic, a lot of the healthcare is done via the phone, filming, making sure how stable is somebody in their exercises and stuff like that. Are there signs of seizures and things like that? That's all video that needs to be analyzed. Wildlife is a very popular one, being able to find, that one's an interesting one for the needle in the haystack queries, being able to find instances of I don't know, deer grazing. There's also, of course, video recommendation of hey, find me something similar to this, things that, companies like TikTok, Meta, Instagram, whatever, are very interested in. And then there's sports analytics, of course, which is very much on the action recognition front. For that one, there is a SoccerNet data set that you simply it's very easy to get, and they send you a bunch with labels. So that one's a good one, SoccerNet. That should cover a bunch of the areas, but I think And video's everywhere, so there's a bunch of different areas that it can be applied to, like
Great.
video analytics.
Yeah, great.
So-
Really interesting. Yeah, also you mentioned vision language models. So these are quite new, right? So as far as I understand, this is just started, right?
Yeah. So vision language models, I think the most popular one is Clip. It's the one we used, which basically works here. There's been some more recently that do video. I haven't not dug deep into them, but they're still in the very nascent stages. But the interesting thing about these, I think for like serverless stuff, is managing the embeddings in terms of it's almost like a vector database. Vector databases are, an interesting thing these days. So maybe there's something there as well to explore on the infrastructure point of view. Like how do you cache the embeddings? How do you, if you want like one tip that like how do you batch the embeddings and then to store them? I think is an interesting question. Like, should you be storing them like close to each other, like where, they're similar to each other, or like should they still be just the sequential frames? Like it's not clear to me, like especially optimizing for the device or reads from the cloud. So it's a little nugget that I thought of throughout my studies. But these are, long story short, yes, these are new models. They're really exciting. I think they're really changed the game for video analysis because of the fact that you can query with natural language. Really exciting stuff. And they work pretty well.
Great. Any more questions, guys?
And feel free to, I didn't put my email, well, there. So there's my email. Obviously, Dimitri has my email, my contact info. If anything comes to mind later, well, happy to take them now, but if not, like, feel free to, email me later as well. More questions? All right.
If
Well,
not,
there's some really good
stop the
questions throughout it.
recording.
So I think there's some really great questions throughout the talk too. I could tell you were all paying attention for what it's worth. So yeah,